Next up, invite John Fragalla from NVIDIA. I'm excited to hear him talk about NVIDIA cloud providers.
Thank you. John Fragalla. Happy to be here. So my role at NVIDIA is actually a storage architect at NVIDIA. And one of the things I'm solely responsible for is the storage architecture and certification of the NVIDIA Cloud Partner Program. And then the previous talks from Alex and Paul was a great segue into what NCP is all about. So Paul presented the scalable design of 1,000 GPUs going up to 4,000 GPUs in this modular approach. This is what the NVIDIA Cloud Partner Program is essentially about, is a reference design based on repeatable technologies from NVIDIA. So when we look at solutions trying to do time to market or time to train, the key thing that we wanted to provide in the NVIDIA Cloud Partner Program is a referenceable architectural design that is repeatable, that could be implemented by our NVIS team for quicker deployment and quicker time to train. And part of this is to look at the scale of the architecture. So when we look at these things, we didn't want to create snowflakes out there that every new deployment is different. So we publish reference architecture designs for how to deploy GPUs at scale. And starting at an initial deployment of 1,000 GPUs, scaling out to 16,000 GPUs. But it's not just about the GPUs and the deployment of the GPUs. It's also the networking that goes in the aspect of it. And there's two aspects of networking that we have reference architecture designs for. It's the GPU to GPU networking, as well as the GPU to storage networking. And a balanced approach between the two is what is essential to ensure that your efficiencies of your GPU is not bottlenecked by any of the key aspects in the architecture. And the other piece of it as well that's all coupled together, you can't forget about software. So software is a key aspect of this to ensure that we have a reference architecture design around the software stack that gets bundled in with the NVIDIA software stack to ensure that when you do this modular growth, you have the ability to deploy the GPUs at scale, manageability, and then provide a solution around security and multi-tenancy, which is inherently part of NCP. It's not just a single tenant, it's multiple tenants. With multiple tenants doing simultaneous training, and it's multiple tenants doing simultaneous checkpoint. So as what Alex and Paul mentioned earlier, the key aspect to that is providing a storage solution our NVIDIA Cloud Partner Program could then leverage as part of this solution. And we have used and certified the DDN platform not just because of their performance, not just because of their resiliency, but also their security features that I'll touch on to this as well. So when we look at this, we're trying to then build basically AI factories referencing the NVIDIA Cloud Partner reference architectures from anywhere from deployment for a cloud provider, as well as quicker time to market. So when you look at a reference architecture design, NVIDIA has published reference architecture designs for the compute node. This is based on HGX, OVX, MGX platforms. We then published reference architecture designs for the GPU to GPU communication. This is based on either InfiniBand or Spectrum Ethernet. Then the converged network, which we call north-south. This is where the high-performance storage gets connected to allow GPUs to communicate directly to the high-performance storage tier. And then the converged network also includes the out-of-band management. What we have done in the NCP program is create an extensive certification program to then onboard and certify high-performance storage partners. And DDN has been the forefront of that for the NCP program as well. They have gone through extensive testing, rigorous analysis of not just performance, but resiliency, reliability, scale, security, and data services. And they have met all these requirements for the NVIDIA Cloud Partner Program. The other key aspect of it, as we touched on this a bit more, is inherently you have to understand that there's going to be multiple tenants being deployed at each NCP deployment. So one of the key aspects that multi-tenancy requires is the ability that one tenant is running, has no idea a second or third or fourth tenant is simultaneously running on the same infrastructure, because the network does isolation, the GPUs isolate their applications to specific tenants, and then the storage has to be a big part of that data isolation and security between each tenant. The ability to tear down, ability to create tenants on the fly, and ensure that security is an inherent model of not just for tenant creation, but for training. When you look at a high-performance storage architecture that we have architected within the NCP program, we can't ignore the fact that there's another tier that exists there. And that tier is what we call a data lake tier. This data lake tier is what we say is provided by the CSP that's deploying the NCP reference architecture. This tier is basically an S3 or an NFS tier. This is where all the onboarding of tenants and users upload their data to. But for the high-performance storage tier, this is where the bulk of the work comes in for model load, model training, model checkpointing. And one of the key aspects that the high-performance storage tier has to adhere to is the connector tools to facilitate data migration between the data lake tier and the high-performance storage tier. Because when you want to start doing real work on GPUs for training, and this is also for LLMs doing single modality and multimodality, you want to make sure that that gets staged in the high-performance tier to ensure that the efficiency of your GPUs remains high. So connector tools to migrate data in between these two tiers is key as one of the key attributes of the high-performance storage tier that DDN adheres to. So let's look at an overall use case, an LLM training flow. So this is assuming that the data set and the models are loaded into the high-performance storage tier. The first aspect is you want to do a model load. And then from the model load is where the bulk of your work you want to reside on is training. That's where exactly what you want to do is a high efficiency of GPU utilization during training. But as Paul mentioned earlier as well, things do fail at scale, and periodically you do have to checkpoint. Based on the model size of how many bytes per parameter in a model and the data set size, you periodically have to checkpoint. The key aspect of checkpointing is to size the storage system to ensure that you do that as quickly as possible. The one thing you do not want to do is then do length of time to do checkpoint, and then your important resources of GPU is sitting idle for a synchronous checkpoint. So you want to make sure your storage is sized adequately for these checkpoints. And then over time, you do periodic checkpoints as you do continuous training. And the time and frequency of that checkpoint depends on the size of the model, the scale of the number of GPUs, and how frequently you want to go back in terms of previous checkpoint, depending on if there's a failure. And then there's two aspects of it, is that great, you complete the training and you are now ready to go into production with that model, or if there's a failure, you just got to reload from the checkpoint from the high-performance storage tier. So you look at this from a I/O perspective. There's actually three phases we talked about. And let's talk about it from an I/O perspective. When you look at a model and data set load, from a file system perspective, it's essentially a read, sequential read. Then there's this big gap that looks like there is no I/O that happens during the compute phase. It depends on the data set and depends on the size of the model and depends if that data set gets cached locally on the GPU host memory. Typically, if your data set is cached, the I/O during training is minimal. If your data set is large, like for multimodality, and your data cannot be cached, there's going to be much more onerous of I/O performance during training, which then sizes to another aspect of storage bandwidth beyond just single modality of training. And then with a synchronous checkpoint, you have this write bandwidth. And essentially, you could think of it as a sequential write. And this is all key to size your storage system for the ultimate goal is high GPU utilization for training. So let's talk about a little bit more on the training aspect, and I zoomed in this graph on the training and what that would look like for I/O. So as we zoomed in on the graph in the previous slide, so in the previous slide we have the compute in green. Let's see if this works. It looks like there's no I/O. But if I zoom in on that one particular graph, you see the GPU graph on the top is 100% utilized, which is the ultimate goal for training. And then when you zoom in, there is I/O that still occurs to the backend storage subsystem during training. And depending on what that I/O size is, if the majority of your data is cached, the I/O will be minimal, and it'll probably be random I/O at best, and latency is important for that. So not just throughput is critical, latency is critical as well. And then the other aspect, if your data set is large, this graph would then become more of a throughput graph with GPU utilization. So the key aspect of it is if you undersize your high-performance storage tier for a training model that is multimodality and you size it for single modality, you're going to starve your GPUs. So to understand what type of model you're training and your data set is key for overall storage sizing, not just for model load, not for checkpointing, but the overall I/O scheme. Let's talk a little bit more about checkpoint and model load, and what that means from a data set perspective when you look at sizing your storage subsystem. So on the left, you have a checkpoint table, and on the right, you have the model load table. When you look at a checkpoint, and this is an example of a synchronous checkpoint, there's this parameter in a model that you size called tensor parallel size. This is basically the number of GPUs in an NVLink domain. With that, you size that, let's say in hypothetical, HGX, H100, or 200, there's 8 GPUs in an NVLink domain. You set your tensor parallel size to 8. That means that if you take an example of a 175 billion parameter model, on average, it's 14 bytes per parameter. So you're going from anywhere from a 2.4 data set checkpoint size to a 14 terabyte checkpoint size to a trillion model. But let's say you have an example of 4,000 GPUs. Not all 4,000 GPUs are going to participate in your checkpoint. The tensor parallel size dictates how many of those GPUs will be participating in that checkpoint. So in this example, it's 1/8 of those GPUs because the NVLink domain is 8. So that means that one GPU out of 8 could actually do a checkpoint because they all do the shared memory because of the NVLink domain, and you do a checkpoint. What that means per GPU of the aggregate data size, let's take an example, the largest ones, the 1 trillion parameter, that's 14 terabyte aggregate data set size. That means that a per GPU is around 28 gigabytes per GPU to do a checkpoint. Now let's take down the flip side and what that means for model load. Model load is all GPUs participate in loading the model in the data set. When you do that and your tensor parallel size is still set to 8, your aggregate data set size is 8 times that size. So for example, the 1 terabyte parameter size for a model load is 14 terabytes. 8 times that's 110 terabyte data set size for a model load. But if you normalize that down to a per GPU data set, it's exactly the same as a checkpoint, 28 gigabytes per GPU. So that's when you have to look at not of sizing for the checkpoint bandwidth, is understanding your tensor parallel size domain and understand the bandwidth per GPU or bandwidth per NVLink domain is what's needed, a critical size for the right bandwidth. And the load balance and the load of the model has to balance reads from all GPUs loading that model. Now this is just for NCP, one tenant. Just imagine multiple tenants doing this simultaneously. And this is where the storage subsystem needs to also leverage that if multiple tenants hit the back end, performance shouldn't be throttled back, down, or forth between each tenant. It should be predictable performance between each tenant. And that's where DDN has showcased well in the certification process as well. And these are just guides in terms of what we provide as guides for high-performance storage sizing based on these two metrics called better and best. Let's describe what better and best means from an NVIDIA perspective. So when I think of better, or when NVIDIA thinks of better, the guidance we have is the models are in the order of magnitude billion size. The data set is predominantly cached in the GPU host memory. And the modality of each model is single modality and multiple tenants. And that's usually a guide that we say is under the better category. The best category is, again, multiple tenants. You have an order of magnitude trillions of parameters. Data set size is not always cached in GPU host memory, which means that, as we mentioned earlier, that there's going to be more I/O during not just checkpoint and model load, but more I/O during training, which means that that bandwidth number goes substantially higher to compensate for the data not being cached locally to GPU host memory. And that's where the categories of guidance between better and best. Not saying these are absolute guidance that all of our CSPs leveraging the NCP architecture follows. These are just guidance. And so it could be much higher than that depending on how many tenants they actually have active altogether. So now let's talk about the advantages that DDN has when it comes to the use case of model load and checkpointing, and if you undersize the storage. So let's look at concentrate at the blue labels first. So the blue label here, the blue graph here, and the blue graph here. What the blue graph tells you is that a storage system is not sized appropriately. What that means is that the model load and the data load takes substantially longer for the GPU. You might say, okay, I do that once. I don't really care. Okay. But then let's say your checkpoint is also then periodically checkpointing. And if you're doing synchronous checkpoints, training halts and GPU utilization drops to nothing until the checkpoint is complete. And if you undersize your checkpoint, that means your valuable resources of GPUs are sitting idle. And that's not where you want to be in terms of training and GPU utilization. What you want is your GPU utilization high almost all the time. So when you undersize this or you have a storage platform not sized or balanced for reads and writes, this could be a problem for efficiency and use cases for your GPUs. But if you look at what DDN provides for NCPs, they have the ability to scale not just for writes, but for reads to ensure that model loads happens as quickly as possible, and then the checkpoints complete as quickly as possible. And this is the time where you say, right here in the green, this is the amount of efficiency gain you get using DDN as a high-performance storage tier. The other aspect that DDN has showcased for NCP deployments is not just bandwidth, not just performance, it's security. Multi-tenancy is a critical aspect for the NCP reference architecture design. Within the DDN platform, they have the ability to authenticate clients to the particular data store isolated for each tenant. And the way they do that, they do keys, they do security, they do encryption. They have access controls to ensure that the right tenants are accessing the right data store at any given time, and no crossover or no visibility into any other traffic that goes on to any other data store at all. It's completely isolated. And the ability to do forensic auditing on their system to ensure that no one is trying to break through the security model is key. And this is all aspects that they have done to deploy to advance the NCP deployments, not just for performance, which we know DDN is great at, but the security, multi-tenancy, and encryption side of it. Thanks for your time.
Thank you, John.